In this video, we will discuss the stiffness modification of structures. Before we discuss stiffness modifications, we need to understand what exactly is stiffness. The stiffness of an elastic body is a measure of resistance to deformation. This resistance to deformation is related to the modulus of elasticity E and the moment of inertia I of a member. E is a material property. In the construction world, we usually refer to this material as concrete or steel. I is a geometric property, and this will depend on the geometry of the member. For a rectangular beam section, the moment of inertia is BD cubed over 12. B is basically the width of the member, while D is the depth of the member. Whenever we want to design a building using designing softwares such as ETA, Start Pro, etc., you are required to change the stiffness of structural members, also known as the crack section of the structural member. But why is this so? We know that in reality, all concrete cracks, and when concrete cracks, the stiffness reduces. If we don't account for this crack, the design might be more rigid than what is actually needed. The walls, the columns, and the beams will be more rigid or more reinforced than what is needed. How does this happen? When our structure cracks, it will also change the force distribution in the structure. And if you don't capture the crack moment of inertia, especially when designing large structures, your design will be more rigid than what is needed. Let us see an example. Let us assume we have a beam like this, and you have a bending moment like this for the beam. Considering the moment of inertia, BD cubed over 12, ignoring cracking on the beam, these are the reinforcements on the beam after your design. On site, this beam will crack. When I say crack, I'm not talking about large cracks. I mean micro cracks. The tension in the members will cause these micro cracks to appear. This is because beams are tension members, and micro cracks tend to appear more on tension members. This is why micro cracks appear more on beams than columns, because beams are tension members, while columns are compression members. When this beam cracks, the stiffness reduces, the physicity reduces, and the moment of inertia also reduces. Due to this, it won't develop S moment here in reality, as you can see on the screen. It will be less than S. The less the physicity, the less force it will attract. The beam will sag more. Therefore, the moment in the mid part of the cracked beam will be more than the uncracked beam. This is like you saying, this is like two people holding a blanket, and your hands are not strong enough to hold it. When you release your hands, your sagging increases and the force at your support reduces. Therefore, when you consider cracking, the steel at the bottom part of the beam increases due to a higher moment at the bottom mid part of the beam. The steel at the top part of the beam reduces due to the lower moment generated at the support of the beam. From these images, you can see that instead of using 8 number of steel bars in the beam when we didn't consider the crack section, the number of bars in the beam was reduced to 6 after considering the crack section. This is why we account for the crack section of members in our structural analysis and design. To capture these cracks in our analysis, most building codes suggest a value to modify the stiffness of our structural members to account for these cracks. This is based on studies done by various engineers over the years. The beam inertia is 0.35 Ig, which is 35% of the gross area or the initial area of the beam should be considered after the crack. This means you are only taking 35% of the stiffness. The column inertia is 0.70 Ig, that is 70% of the gross area or the initial area of the column should be considered after cracking. This is to say you are taking 70% of its stiffness because columns crack less when compared to beams. The wall inertia is 0.70 Ig, which means you are taking 70% of the gross area or initial area of the column should be considered after the crack has occurred. This is to say you are taking 70% of its stiffness because walls also crack less when compared to beam. Walls and columns are similar because they are both compression members. Finally, for slabs, the inertia is 0.25 Ig, which is 25% of the gross or the initial area of the slab should be considered after the crack. So therefore, if you don't consider this stiffness modification or cracking of concrete, you will get lesser deflation in your structural analysis. But in reality, the deflation is more because it is cracking. This is the significance of introducing stiffness modification into our structural analysis.